When we talk about building a model and figuring out whether it's a good model or not, whether it's too complex or too simple, we make decisions based on what we call the model accuracy or the goodness of fit. So, say we have some estimated model f hat. The question is it a good model for our data? Now, depending on how we measure the goodness of fit, we do one thing or another. So, let's say in general we use some function a that gives us a measure of how good the model is. We will see later some examples. We typically talk in either positive terms, so the model accuracy is something that we want to maximize. That's, for example, the fraction of correctly classified instances in a classification problem. We want this to be high. We're measuring the accuracy of the model. And sometimes we talk about the error of the model, kind of in a negative way. So we want to minimize the error. For example, the average magnitude of the error in regression. So in general, let's talk about model accuracy to refer to one thing or another. It's just a way of measuring the goodness of it, how good the model is. So, okay, we have a certain way of measuring that. Again, let's call it A. How do we do it? Well, we could use the training set, right? We could use the training data, which are again up to n observations of the tuples y I, so the y, the response for the observation I, and all the predictors for the observation I. And so we could compute something like in here, what is the accuracy of the estimated model given the training data. So for example, if we're looking into a regression problem, we could go through all n observations of the training set and compute something like the difference between the estimated value and the true value squared. So a square deviation between the observations and the true value. The thing is that this is always too optimistic because it's based on the data that we're using to train the model. So of course it's going to have a small error. The accuracy is going to be high because we are trying to precisely maximize the accuracy of the model in the training set. It could be that we are just overfitting. And in the end, it could be something like we have a perfect model. The goodness of fit is perfect because we go through all the n observations, but still, it's not a good model. So the accuracy of the model in the training set, it's normally too optimistic. We have to look into something else. Okay, we could look into new data, unseen data, new test data. So let's say we have some new observation over here that is not in the training set. And we want to use that to estimate, in general, the accuracy of the model. So not the accuracy of the model on the training set, or for that purpose on any data set at all, but just the accuracy of the model for the hypothetical population we are thinking about, the population from which we got this training set. And so this new test data, in principle, should be sampled from the same population as the training set, right? And ideally, it should be all the other elements in the population. So if we want to build a model F for a certain population, then ideally we should see how well the model behaves or how well the model performs or how well it fits all the other data in the population. That's the idea. So let's say we have a training data set over here in gray. Then we can fit the model, use the data to fit the model. We have it over here, F hat, and we can check the accuracy of the model, check the goodness of fit of this model while using again the training set. Now, this would give us the accuracy of the model given the training set. We know this can be improved just with a better class of models, a better set of features, or just by overfitting. So this is not a really good idea. This is precisely the criterion we use or algorithms use to come up with this model in the first place. That's not a good idea to look at in order to determine how good the model is. So what we should do is get some test data different from the training data and use that one to check the model accuracy and come up with an estimate of how good the model is in general, the true capability of the model regardless of the training data. Let's see some example. So over here, we have a reality, a certain relationship between a y and an x. Let's say it looks something like this in black over here. This is reality. Again, normally we don't know this, but just for illustration, let's say this is what it looks like. And then we have some observations. And then over here on the right, we have a few terms. First of all, we have a dashed line for the reducible error. And this is telling us that regardless of what model we build of y as a function of x, there's always going to be some amount of irreducible error that we cannot get rid of. Why? Because the observations do not lie perfectly on the line. Here, there is some degree of randomness in the process. So regardless of how good the model is, this randomness is always going to be in there. The second term is here in gray, and it's telling us that as the model complexity increases, so as we allow the model to be more and more complex and to wiggle more around the data points to try to accommodate all the training data, the error of the model is going to decrease. So the accuracy of the model given the training data is going to be better. We are reducing the error. And then somehow we're going to see that the accuracy of the model, the true capability of the model for the population of data, yes, it's going to start decreasing as we make the model more complex, as we allow the model to go through the data points. But then at some point, the error is going to increase because we're going to start overfitting. We're going to start building a model not of reality, but a model of the data set we have. Let's see some examples. So let's say we just build a linear model, something like this straight line in orange. It's probably a too simple model because it's, for example, missing the non-linearity in the relationship, right? So it's a model that in terms of the accuracy on the training set is going to have a quite high error. And in terms of the accuracy in general of the model, it's also going to have a high error. It's really not a good model. So we could try and allow it to be a little bit more complex to go better through the data points. So we could build a model like the blue one over here that does capture the non-linearity in the relationship. So now this model, in terms of error in the training data, we see it's smaller than the orange one. It's a better model for the training data. And it turns out to also be a better model for reality in general. So the accuracy of the model is better over here for the blue model. It's better than the orange one. But at some point, we might be increasing the complexity even further and come up with a model like the one in green over here that we see is just wiggling around the data set just to try and go through all observations. Now we know this model is probably too complex. It does a very good job at trying to build a model around the data. The error on the training set is very small, but the error on reality, the error on new data is very high. It's not a good model of reality. It's too complex. For any given observation in X, it's going to have a higher error than the blue one. And so this is again a illustration of the trade-off between the complexity of the model and how well it performs on the training set as opposed to how it performs on unseen data, on the reality. And so it's all about finding the balance, the sweet spot over here. Let's see another example. In this case, we have a reality that is already almost a linear relationship between y and x. Reality is almost linear. Again, we have a certain amount of irreducible error, and we're going to see that, for example, with this simple model, well, it looks like we already have a kind of okay model. Yes, it's not perfect, it's not exactly a model of reality, but it's pretty close to it, and that's going to be enough. So in terms of the error on the training data, it's already low. And then in terms of how well it performs on new data, on unseen data, we see that it's also a very good model. It's a good model for reality. We could say, okay, let's try and add some little non-linearity, this blue model in here, to try and get even closer to reality. And then we see that, yes, it probably is closer to reality than the orange one, but in practice, the difference is not so big. Yes, in the training set it's a little bit smaller. Even in reality, it's a little bit smaller, the error, but it might not be worth it to add this extra layer of complexity, this extra level of complexity, because it's going to be more difficult to understand and reason about the relationship between X and Y. And then, of course, again, we could go with something even more complex, this green model over here that just tries to wiggle as much as possible to go through all the points. In the end, yeah, it manages to reduce the error on the training data, but it got a very high error on unseen data. It's not a good model for reality. And so this is again an overfitted model. And in this case, we see that already a very simple model, just a straight line, seems to be good enough. And so what we have to keep in mind here is that we could always, in principle, make the model better for the given data. That doesn't mean that it's a good model for reality. At some point, the model starts overfitting, and the error of the model on new data is going to start increasing. The model is not going to be good for modern reality. So again, all models are wrong, but some are useful, or some are more useful than others. All these models that we are seeing in these pictures, the blue one, the green one, the orange one, they are all wrong. They are not a model for reality, but some of them are useful, some of them are not. That's the point. And in order to better understand all this, it's useful if we think about the bias variance trade-off. So think about the process of fitting a model. We have some training data set, and then based on that, we choose the specific coefficients for the model. We choose the specific model. And so one might think about, well, what happens if we used a different training set? We would have chosen a different model. And if we choose yet another training data set, then that might lead to yet another different model. So one can think about what is the variability in the model across different training data sets. So what happens in the final model depending on the training data we use to fit the model. And that leads to two different concepts, the bias and the variance. The bias refers to the inability of the final model to represent the underlying data, the underlying process. So we know that this is going to be reduced with higher model complexity. The more we allow the model to accommodate to the training data set, then the better it's going to go through all the observations, and then the bias is going to be lower. But it could be the case that increasing the model complexity also increases the variability of the model or the dependence of the model on the training data. And that's what variance refers to. Variance refers to how variable the model is with respect to the training data used to fit the model. So if we increase the model complexity, the model can be a lot different depending on the very specific data set we use to fit it. And if we increase the size of the data set or the diversity of the data set, then what we're going to see is that the variance reduces, because then the model or the fitting process is more aware of what reality really looks like in order to fit the model that doesn't just go through the data points, but tries to understand or model the underlying reality. So we can think about it again in terms of the expected deviation between a prediction and the true value. And in particular, we're going to talk about the expectation over different training data sets. So what do we expect of the square deviation between the prediction of a model and the true value for that observation? And then what happens across training sets? Well, we saw that we have two components. The first one is the reducible error, and the second one is the irreducible error. Now, what we see here is that the reducible error can be further decomposed into two components, a green and light blue here. The first component in green is the bias, and it's precisely this expression over here. So it's telling us what is the distance or the square deviation between the true value and the expected value across training sets. So if we take on the one hand the true value, and on the other hand, what do we expect from any model given any training data set, we get the deviation. That's the bias. Ideally, we want this to be 0. So meaning on average, any model is going to give us the true value. And then we have the second component in blue, which is the variance. So what is the distance between the true value and the expected value again, but squared? So in this case, this is measuring a variance. So how much variation do we have in that distance between the true value and the predicted value? So you can think about it again in terms of bias and variance, plus of course the reducible error. So let's take a look again at the examples we had. So in black here we had the true model or reality, and then we had 3 different models in orange, blue, and green. And over here on the right, we have, as a function of the complexity of the model, what is the accuracy of the model in terms of error. So we see that as we increase the complexity, the error decreases. At some point, we start overfitting and the error increases for new data. And so we can also plot here variance and bias, and it looks something like this. So as the model is more and more complex, as we allow it to wiggle more to go through the data points, the bias is going to reduce. It will go through the observed data, but the model will be very variable. It will have a very high variance, meaning that, for example, in the green model over here, it looks like this for this training data set. If we change the training data set, the model is going to look completely different to this one, and it's going to have a high variance. The model varies a lot across training sets. So what would be the optimal model? Somewhere around here, the one minimizing the error on new data. Let's see the second example. So we have here something that is more linear, and we have over here what the accuracy of the model is on new data. So we see that the error basically with pretty much any model is going to be low, and then it increases as we increase model complexity because it's going to start again overfitting. So what about bias and variance? Well, pretty much the same. Any model is going to have a low bias because the relationship is pretty much linear. We don't need the extra complexity. A linear model is enough. However, if we start increasing complexity, we see that the bias remains more or less the same, but the variance will increase a lot, meaning that, again, any different training set is going to return a very different green model. The orange model and the blue model will be more or less the same, will be very similar regardless of the training data, but the green one will vary a lot. And so again, what the optimal model is, it would be somewhere around here, the one minimizing the error on new test data. And that would be a simple model. So we can think about it again in terms of how far we are from a bullseye. And in this case, we think about every point over here as a model trained on a different training set. So again, the optimal model would be somewhere around the bullseye. That's what we're targeting. But in reality, we have a model that is a little bit away from it. What situations could we have over replications of the training process? So if we use different training data? Well, over here, we have a case in which we have a high bias because on average, the models are around here, and that's different from the bullseye. So regardless of how much variation there is, the bias is high. On average, we are not in the center of the target. And also in this case, we have a high variance because for any given training set, we might have a model that is all around the place, and this is not good. In the second case, we have, again, a high bias because on average, the models are around there, and that's different from the optimal model. And we have a low variance. So regardless of which actual training data we use, the models are quite similar to each other. In the third picture, we have low bias because on average we are hitting the bullseye, but any given model is going to be very different from the others depending on which dataset we use. So we have a high variance. And then of course we want to have something like this in which we have a low bias, we on average hit the bullseye, and we don't have a lot of variation across different training sets. The models are robust to variations in the training data. So this would be the perfect situation. You might wonder, where is overfitting in this picture? Overfitting is the case in which the bias of the model is very low because it does go through the training observations, but it would change completely if we had a different data set. So it would be low bias and high variance. It would be this situation over here. And we could think about kind of the opposite situation in which we have a model that it's way too simple. It does not go through all the observations. It's actually far from it, but it doesn't matter which training data we use for it because it's not going to vary too much. It's a model that doesn't fit the data right. It doesn't vary too much. That's a high bias and a low variance. It would be something like this, underfitting. It's a model that still needs a little bit more complexity to hit the right spot. And so again, everything in fitted models is about trade-offs. And we can think about trade-offs about model complexity. So we see that the more complex the model, usually the more difficult it is to interpret, to really understand what's going on. If we try to open the box and see what's going on in the model, it's going to be quite hard for certain classes of models and for certain complexities. And we might be looking for kind of the opposite, something that is, a good model, but simple enough to allow us to make or to gather new insights and understand what reality is doing. And we might also think in terms of the training and test error. So we know that as we increase the model complexity, sure, the training error is going to go down. It's just about adding more complexity to the model. But at some point, it's going to start overfitting. So the test error will decrease as we increase the model complexity until some point in which we have just the right amount of complexity. And beyond that, the test error will increase because we are overfitting. So it's again about finding the spot. And we could also think in terms of how much variation do we have across different training sets, or how robust the model is to different training sets. And we saw that as we increase the model complexity, the bias will be lower. So we are expected to get closer to the true values, but the variance will also increase. The model will be completely different. So it's again about finding the right amount of bias and the right amount of variance. Okay, good. It's about trade-offs. But how do we actually make a decision about model complexity? What do we look at? Let's see, we could look into the train error, right? We could compute some measure of accuracy of the model given the training data, but we saw that it's probably too optimistic because that's precisely what we are optimizing for when choosing a specific model. All right, we can have some test error, the accuracy of the model, but that cannot be computed because we don't have access to all the instances in the population. This is impossible. So what do? Well, the best option and the kind of agreed upon solution to the problem is to use a large designated test dataset. So a new set of M observations, normally M is much smaller than the observations we have in the training set, but something that is still big enough, and of course representing the same population as the training set, such that what we do is compute the accuracy of the model given that test data, and we use that to estimate the accuracy of the model on unseen data. So it's a separate set of data that we never use in the training process. We never look into it. We never make decisions based on it. The training process never looks into that test data. It's something that we use only at the very end when we have the model to see how well it works. And so the model and the process to fit it should always remain blind to the test data. Why? Because if we make any decision based on the accuracy of the model on test data, either before training or after training or during training, we might be falling for overfitting and we just wouldn't notice. So any decision whatsoever that is going to affect the model or what model ultimately fits the data, it cannot be based on the test data. The test data is only to use at the very end to see how well the model behaves, how well it performs, and that's it. We don't use that new knowledge to go back and change the model again. The problem is, sure, more data, but more data is not always available, or it's too expensive, or it's just plain impossible to get new data. So what do we do in those cases? Well, there's still a range of statistics that we can use to see how well the model performs given the training data, and they try to somehow adjust for the complexity of the model. So the idea is that if we have two models and we have to choose between one or the other, perhaps one is simple and the other one is complex, what we can do is compute one of the statistics and choose the one that minimizes the statistic, one that minimizes the criterion. And we typically talk about two, the Akaike Information Criterion, or AIC, and the Bayesian Information Criterion, or BIC. And they're very similar. So the idea in general is that we compute the likelihood of the model given the training data. The likelihood is essentially the probability of observing the data under this model. And so what we have is the likelihood over here, and we have another term that relates to P, to the number of parameters. And so how do we minimize the archaic information criterion? Well, one of two ways, either using a small number of parameters or having a model that fits the data very well. And it's again about the balance between the two of them, between P and the likelihood of the model. And then the Bayesian information criterion, it's very similar. You see, it's pretty much the same, but incorporates this other term, which relates to the amount of data we use to train the model. And the idea is the same. We choose the model that minimizes the BIC. So how can it be small? Well, it can be small if we use a small data set, or if we use a small number of features, or if we have a very high likelihood. So regardless of whether we have test data or not, we could always look into general statistics like AIC and BIC that one way or another try to adjust for the complexity of the model. So if we have a model that is overfitted, yes, it will have a very high likelihood, so it would lead to a very low AIC, but it would have a very high P. So still the AIC score will be high, and this would not be a good model compared to something that is simpler. And so we have things like the archaic information criterion, the Bayesian information criterion. Those are good alternatives because they are generic and they have nice theoretical properties that we will not get into here. But always the best measure of model accuracy depends on the particular problem, depends on the particular reality we are modeling. And this is again a place where we have to apply domain knowledge. It depends on our specific case. In many cases, this is going to imply the use of ad hoc measures. So if we're building a model for whatever reality, it's very common to find that we are going to look into a very specific criterion to select whether a model is good or not, or to select between two models. And those measures are going to be completely ad hoc. We have to develop them on a case-by-case basis. Unfortunately, that usually implies that we are going to have a test set on which we can compute those measures, those ad hoc measures. The good thing about a test set is that it's going to allow us to compute any statistic about model accuracy whatsoever, absolutely anything. And so sometimes if we have to look for something very specific, we are going to need a test set. And then for different statistical learning tasks, regression, classification, and different types of classification, etc., here in this course, we're going to cover the typical measures we use for the accuracy of the model or the goodness of fit, but we will also talk about different ways in which we can try to have a better description of the goodness of fit of a model that fits better our purpose or our case study, our problem, our reality.